Okay. Hello, everybody. I hope you enjoyed that performance out there. It was like pretty amazing. Welcome to our event for tonight. I've been given the wonderful honor of introducing our co-founder, president, and CEO, Kim Davidson, to kick off the event. Please welcome Kim to the stage.
Welcome, everyone. I'm super pleased and excited to be introducing the Houdini 17 launch event. We're here in Montreal, which has a rich history in computer graphics, animation, a thriving community in TV and advertising, film, and games. I'm so proud of my SideFX team. They're an amazing group. I'm so proud of them, but really, it's you, the artists and animators, that inspire them and us to improve Houdini each and every day. Improving Houdini involves us and you. It's a team sport, really. So thank you. Thank you for improving Houdini by inspiring, pushing, motivating us, and hopefully for many, many more years. And with that, we're going to show you Houdini 17, and I'd like to I'd like to introduce the co-presenters tonight. Can you cut that out on the thing? Cristin, Barghiel, and Scott Keating. Thanks, boys.
Thank you, Kim, and welcome everyone. Welcome to the launch of Houdini 17, which is a major release in more ways than one. First of all, it's the heaviest release in terms of VFX feature in recent SideFX history, with the greatest emphasis going towards fluids, rigid body dynamics, and something completely new, a multi-physics engine called VELLUM. But if you've been with us for a while now, you'll know that our community is growing fast and worldwide, and is asking us for more, which is great. More in VFX, but also more beyond VFX, and that excites us, and we want to help. Now, nobody needs to worry that we'll ever forget our VFX roots. That's never going to happen. But we do want to help you guys look into character, modeling, lighting, motion graphics, gaming, all these other aspects of the CG pipeline that go well with Houdini's proceduralism. And so we're committed to building that platform for Houdini to address this broader spectrum. All right. We have a big show for you tonight, so let's begin with the first one, VELLUM. So VELLUM is a hardware-accelerated multi-physics engine. It is designed from the start with high performance in mind. It starts with very fast cloth, which was the original impetus behind it, actually, and it extends to hair, soft bodies, and grains, and puts it all together. It's based on a flavor of position-based dynamics called XBBD, which keeps the math light and easy and fun and stable. It's written in OpenCL, which gives it that extra GPU kick and performance that everyone wants. Look at VELLUM because it is a sign of things to come. This is only its first iteration, but the vision and the architecture behind it go far beyond what you'll see today. And although it's fresh code, it's already used in production, and people are praising it for the performance, the robustness, and believe it or not, for the fun of using it. I guess that's a good sign. So I'm going to ask Scott to take us through VELLUM. Scott.
Okay, thank you, Cristin. Right, so as Cristin just mentioned, I'm Scott, by the way. I'm going to talk very fast. We have a lot of things to show. So as Cristin was saying, the VELLUM project started with a target on cloth on characters. And that really meant that we wanted to obviously make it fast. You wanted to be able to iterate as much as possible. We wanted to make sure it was robust. So if you hit play on a simulation, sometime later you got the result of that simulation. We don't want it to choke on things. So here's just an example of this character wearing this draped clothing, multiple layers. As Cristin mentioned before, OpenCL accelerated, so a focus on speed, but then also the flexibility that you expect from a Houdini solver. So to support some of this, we did build some interesting tools. So here you see what we call a paneling and draping workflow, where essentially you build up clothing and stitch it together. Now looking at this, you might think like, well, this is for designing clothes. And in some sense it is, but really it's a prototyping tool. It's a way of quickly get a character in clothes so you can start prototyping your effects, prototyping something before all of the actual clothing is designed. But you can imagine that this is sort of a first step on a path toward a fully implemented clothing designer. So fast and stable. So here's an example of something like 200 and something pieces of cloth falling on this torus and stacking up, which in a lot of ways is the worst case scenario for almost any kind of simulation tool. But you can see that it's staying nice and stable. And part of the way it's doing that is that we took some of the lessons we already learned from things like bullet and grains and introduced the idea of sleeping. So sheets on the bottom that are no longer really, adding anything to the simulation basically become collision objects for the layers above. And here's just a slice of that simulation, so you can see all of the layers stacked up and how they're completely resolving any self-intersections and so on. Also, you can check out the solve times there, which are nice and fast even at the end of the simulation. So underlying all this is the idea of a constraint system, VELLUM constraints. And again, we sort of looked at some of our other solvers to add some modern ideas to this of how we would deal with VELLUM constraints. So here we have a piece of geometry on the left and the constraint geometry on the right. And you cannot show a cloth solver without showing at least one flag. This is like, it's an industry standard flag. So on the right, that's the actual constraint geometry. And again, we took some cues from Bullet, the idea that the geometry would ride alongside the actual simulation geometry. And that's where you could do all your work. That's where the attributes would be stored. That's where you would actually alter the geometry in order to create new types of constraints. So most of this work, you can see here some of the VELLUM nodes, is actually done in SOPs. It's actually done before it gets into the VELLUM solver. So here you can see we have a bunch of new nodes, VELLUM constraints, and all of these are basically building two pieces of geometry, the actual geometry and then this second set of collision geometry that rides alongside it. And it actually flows through these wires. So we started using these sort of 3 input, 3 output nodes so that you can have a nice clean network without having to pass data around in complicated ways. And then we've also made some improvements to the network editor so that when you drop a node on these chains, you automatically connect up all 3 wires. So you're not managing that data. But again, going back to the constraints. So here's just a close-up of that flag geometry and the constraints that are underlying. You see these diagonal sort of lines connecting everything. And you can imagine these constraints as a place to store information that the simulation needs. Things like how much bend is allowed, how much stretch is allowed, where should things break, and how should they break. And here's just an example of some of these attributes stored on that geometry presented now as just a visualization. And these actually become extremely useful when you're working up your simulation, especially as you start adding things like dynamic constraints. So here's an example of wires and cloth. And so when the wires touch the cloth, they attach dynamically. And again, because we're using this idea of constraint geometry, it's actually very easy to generate and destroy geometry in Houdini. It's one of the great things about it. So here you can see 2 different types. One where the wires stick and stay stuck forever, they become glued, and the second where they even become detached later based on some forces. In this case, it's the amount of stretch holding the wires to the cloth. And again, it's really important to be able to understand what's happening behind the scenes. So this is an example of a node called VELLUM post-process. And the point of this node is that it happens after the simulation. And the reason for that is that that means you can write your simulation to disk, put it on your render farm, whatever you're going to do with it, and then afterwards actually still be able to analyze all the information in a useful way. So not only is it a post-process to help you dial in things like how much stretch stress is on this particular constraint here, but also do things like clean up unnecessary attributes and process your geometry so it's nice for anything that might happen after the simulation. And then that makes it very easy to set up simulations like this. So here we have wires attached to strings, attached to cloth, all in one simulation, all working together and being broken basically by the strength of this wind and how much stress there is on the various constraints. And something like this is actually very simple to set up. What normally is a very painful process becomes quite easy because you're in SOPs in a place that artists are actually very familiar with working. So let's show an actual example here. So we're just going to use the shelf tools here and turn these two objects into VELLUM objects. And we'll go ahead and hit play. And by the way, in all these demos that you see, anything in the viewport is the actual speed that it simulates in, and then we speed up the UI stuff so you don't have to see me clicking buttons and things. But here we go. So we've got a sphere, we've pinned it, it drops down on the cloth. Let's just go ahead and add some bend stiffness to that sphere so it doesn't just collapse on itself. Hit play. And here's, again, the huge advantage of VELLUM, right? Just the idea of iterating, how quickly you can iterate on something, even simple like this. So next thing we want to do is fracture this cloth. We have some new tools to do that. This is the edge fracture tool. And you can see it just splits up your geometry in sort of an interesting way, and then everything immediately just breaks into pieces. And you can see how I'm building up this SOP chain very quickly and easily here. And this is using the new VELLUM constraints to actually glue this together, to stitch those pieces together. And then finally, if we actually want to add some dynamism to this, we can allow breaking, enable it, and set a threshold. And now our sphere goes ahead and breaks through the cloth. And you'll notice across all these welds and stitches, we properly allow for bend constraints. So everything doesn't look like it's faceted in the sim. It's only after things have torn that it looks that way. And here are just some more high-level examples of tearing cloth, multiple layers of tearing cloth, fast-moving collision objects. And again, the idea here is that you can actually build the tearing into the geometry itself and then art direct exactly how you want this thing to tear over time. And of course, that means you can do things like this. You can have animated collision geometry, and based on the amount of stress on those tears, his pants can tear open like this. And of course, you get the awesome visualization to help you tune those results. But of course, you can also directly manipulate those attributes. So if you want to tear based on a very specific timing, in this case, we're just running a ramp from left to right through the geometry to tear it apart, and you see it tears. And then, of course, again, stressing the idea that understanding the forces behind the scenes and seeing exactly where the tears are happening and how and when they're happening gives you full control over the system and allows you to visualize all of the useful information. It also just kind of looks cool how you can see the stress fly through those parts of the mesh. So, like we said, cloth was the goal. When we started out, it was about cloth, it was about characters, but very quickly, due to the nature of XBBD, it became sort of clear that we could extend this into other areas. It didn't have to be just cloth. It could be things like hair, where you've already seen some wire-type examples earlier. So the nice thing about embedding this workflow in one place like this is that we can also embed it inside the grooming tools. So the grooming tools add things like clumps or stiffness to the groom in order to make the groom look a certain way. And then the VELLUM solver can just pick up those things. So the clumping from the groom becomes clumping in the simulation. Again, all controlled with this geometry between constraints. And you can see that when you get it to a final look, you get this very believable look where different parts of the mane, his beard, his whiskers have different properties, and those are basically inherited from upstream from when the groom was created. And so again, it creates this sort of unified environment where the groom goes straight into the solver. And then soft bodies became another area that was immediately sort of obvious to us once we started playing around with this solver. So you may remember a demo like this from a couple of years ago with these squabs falling into this bowl, and that was done with FEM. This is actually done with something we call strut-based soft bodies. So essentially, we build sort of a scaffold of geometry inside these objects to sort of maintain their volume. So the FEM solver is not going away. The FEM solver is still sort of the king when it comes to pure, realistic simulation for soft bodies. However, the speed, the ability to iterate, and the flexibility of the VELLUM solver definitely makes it a good contender for these types of simulations when you need them really fast, and maybe you don't care if, the squab in the middle doesn't move exactly the way you might like him to. But that's not the only type of volume constraint here. We also have pressure constraints. And so the idea here is that we have these constraints inside of Flip that preserve the volume globally. And so that means that when you press down on one side of the object, the other side is forced to expand. And it's not just a pressure like that. You can see we can also inflate this object from nothing up to full. So there's going to be all kinds of really cool, interesting effects you can get out of this setup. And then, of course, these things all work together. So here's Crag walking. He's being attacked by these balloons. The balloons are dynamically constraining themselves to the animated geometry, but also other balloons. And so, again, these constraints, they all work together. They can create really interesting dynamic simulations. And then finally, there are tetrahedral soft bodies. And so what this means is basically another way of conserving volume inside of an object, except in this case it's locally. So it's more like there's a fluid or something inside there. And in fact, you can kind of imagine this working as a flesh simulation. And you can also imagine that down the road we'll probably be approaching things like flesh simulations using a technology like this. But for the moment, squishy flips. And here at the end, we just want to show a couple of examples of all these things coming together. So here's a strut-based flip colliding with what's essentially hair or wires. We can dynamically add the constraints to stick flip to the web. And then we can also combine the dynamic constraints with tearing constraints on the whole setup to get a very realistic sort of interaction between all of these things. So you might be wondering then about grains, because grains were PBD, and this is XPBD, and the reality is that it's true. Oh, one more thing, I'm sorry. I want to talk about controlling some of these aspects. So here we just have a simulation, again, playing at the speed it actually simulates at. We're just throwing these squab babies at this target. And basically we want it to stick to the target. But we don't want it to stick uniformly. We want to have some control over that. And as you would expect from a Houdini setup, you can very easily do that, and we've actually sort of built this idea into the solver itself. Video paused. So you can see I'm just adding an attribute, scale by attribute, and then I'm just going to paint it on this target here. And we'll just do it directly in the center so it's really obvious where it is. And then we hit play, and as you would expect, squabs can hit the side and not stick, but as they get closer to the center, they stick where we painted the attribute. So this is sort of a silly example, but you can imagine something brushing up against a wall where there's different frictions or different areas are sticky and other ones are not. And plasticity. So a big feature that people always ask for is the ability to sort of bend something and then have it stay bent in that shape, which is essentially what plasticity is. So the VELLUM solver is not great at perfectly rigid things like steel or something like that. However, it is great at things that are sort of a little bit bendy. So you can kind of imagine sheet metal or something here. And here we're actually getting a very nice response from the plasticity. You can see that final sheet, when all the weight of the sphere hits it, it bends it and buckles it permanently. But where it works really nicely is for things like grass, things like hair. And you can see here Crag walking through the grass, leaving footprints, leaving a trail. And so the red areas become compressed. They're at sort of their full plasticity. They stay in that shape. And the other areas are allowed to relax over time. And it gives you a really nice natural look. Sort of an interesting side note of this simulation is that every blade of grass in this simulation is a simulation. Nothing is interpolated. So there's something like 70,000 blades of grass in this simulation. And it basically just runs through it. There's not really major issues to mess around with it. So it's a lot of fun to set things up like this. And now we get to grains. I jumped the gun a little bit, but grains. So again, originally we had grains. They were PBD. But it made a lot of sense to pull that into the VELLUM solver so that you could get new types of interactions that were impossible before, right? Things where grains interact with the cloth. So in this case, the cloth is tearing as it hits the ground because the grains start pushing outward and the pressure causes the tear to happen. So these types of interactions are really, really nice. And now that they're all together, you can create really complicated sims all in one place. Now, there are still reasons to keep the old PBD version of grains around, especially if the grains are completely in isolation from each other. But the huge benefit of having them also in the VELLUM solver is that it allows situations like this where we use basically every type of object together. So we have grains, wires, cloth, and these soft bodies all interacting together in a believable, way, which is really just not possible without a physics multi-solver like this. And now I'm going to invite Cristin back up to the stage.
Thank you, Scott. How does VELLUM look so far? Thank you. Our next chapter is on character development. And some of you know, many of you maybe don't, that extending Houdini's capabilities into animating, rigging, simulating complex characters is actually one of the biggest long-term goals for us. Our company started doing animation and then visual effects and motion graphics and whatnot. Crazy cycle. But anyway, animation has always been dear to us, and so we strive to make it better with every release. We have a wealth of tools and workflows that speak directly to animators and riggers. And this release is no different. In fact, if you look at the scope of development for character, it is only second to the effort that we've put into all those many VFX features into Houdini 17. And that should say a lot about it. We've also noticed something. You know, up until about a year ago, people were just curious about characters in Houdini. But now that's changed. Something has changed. Some of it is the new features that we've added. You know, you have things like post-space deformation and full-body IK and facial auto-rigs, things that everybody's been asking for. But I think it goes beyond that. It's people starting to understand the mentality behind characters in Houdini, the fact that it's actually very accessible to artists, that it makes a lot of sense to riggers. And then there are things like leaps in performance that you'll see in Houdini 17, much cleaner, streamlined workflows that keeps users in once they see those possibilities. So perhaps if you haven't taken a dive into Houdini's character landscape until now, this might be the release to give it a shot. And to show us through all those features, or some of them at least, here is Scott again. Thank you.
So we introduced crowds a couple of releases ago, and our goal with every release since then was to make the crowds more and more believable, let the camera get closer and closer and closer to those crowd agents. And once you get so close, it becomes very obvious that you start to need secondary effects, right? A baked out animation is not going to work in a close-up. They have hair, they have clothes, and so on. So here's just an example of a herd of horse agents, and their manes and hairs all have their own stiffness properties, their own animation, and it works with the RBD ragdoll simulation as well. So you can imagine that you obviously could not bake out this result and just play back an animation. It has to be dynamic. It has to live in a simulation. And so to help with that, we actually started tying the two systems together. So we don't have time to go into all of the crowd tools in 17, but here you can see Agent Unpack, and it's being used to bring a cloth sim and an agent together. And so here we're just going to put down the VELLUM solver, which you'll notice is also a SOP, and just go ahead and hit play. And here's our guy running. His pants sort of fall down over time, which is fine. So we can now go ahead and take our VELLUM constraint node, and basically we're just going to connect some of this clothing to that agent. And that's simply done by selecting some polygons and using it as the group in the VELLUM attach node here. We'll go ahead, attach him up, and hit play. And so really the nice thing here is that this ties directly into the agent workflow. And so now you can see we've got an agent running with cloth. So the idea is that you would hero out some of your crowd agents and you would run a simulation on the results. But when I say a crowd agent, it can genuinely be a large number of agents. So here is a single VELLUM sim of these clowns, they're running. So everything that you see here is simulated in VELLUM. The clothing, the goggles, the toys, even these rigid objects at the end. And so you can see that even though there's a lot of crowd agents here, they're all piling up, it's all working together. And again, a type of simulation that you could not do with a baked out set of animation. This only works if you can run this many characters through the simulation at the same time. But as Cristin said, maybe you want to generate the animation here. A lot of times crowds is just based on motion capture data or something like that. But occasionally you want to get in there and you want to do it using the character tools. And when you think about character animation tools, it's really about the workflow. The tools are definitely important, but almost more important is how you interact as a user with those tools. So we've taken sort of a hard look at a lot of the options in Houdini. We've taken the channel editor here. We've revamped a lot of the UI to simplify it, to make it more obvious for an animator to use. We've added new icons for the various controls that are useful to you. And we've changed the way some of the visualizations for which channel is selected, which channel is not, to make it a bit more obvious. But even more so, we've revamped the way you interact with it, you know, in the scene, the way an artist actually would. So we've revamped the timeline that you can see at the bottom of the screen. We've also given access to animator tools that were always sort of hidden in the channel editor, like this channel list box that you see here. And so this can actually be used directly. Obviously, you select something, it shows up in the channel lister. But you can also do interesting things like just select one in there, select one in the viewport, or filter the results. So for instance, you could type down in the filter there, L star, and only get the controls for the left arm. So even though you've sort of done a broad stroke over all of the controls, you can be sure that you're only going to key the things that are in your filtered list there. So again, just clarifying what is selected, what's going to get a keyframe. And then we've also added some options to the timeline itself, like adding and removing keys directly, or even just grabbing a key with the middle mouse button and shifting it on the timeline directly. So again, it becomes a lot more approachable to the artist. It puts it in the space that they're used to working with in the viewport, and presents the controls in a place that they can easily find them. And along those lines, we also have things for creating channel groups in Houdini. We've had those for a long time, but again, they were kind of buried in a weird place. Now we've added them directly into the parameter pane, so you can click on a folder, create channel groups from folders, create channel groups from selections, and again, the channel group window is now accessible from the main UI down by the timeline. Again, putting the controls into the viewport where the animator actually works. And we've been sort of building up our character tools. At the same time, we've been building up tools for sort of automatically generating them. So for a while now, we've had a biped auto rig, we've had a quadruped auto rig, and now we're adding a facial auto rig into that mix. And the idea here is that an animator or a rigger can quickly rig a face, get a full set of facts to go along with it so you can immediately start using it, but also provide controls on the face for direct manipulation. So you can grab those controls, you can move it around, and we do that by creating these series of sort of mask objects that help control and deform the underlying geometry. And if you're working with this, if you're setting this up, you know, you're not laying down nodes and things like that. Behind the scenes, everything is a node. But presented to the user is a nice interface like this that guides you through the process of creating the facial rig. You can see that it's an extension of the biped and quadruped modules. So now we have these two face modules to get you up and running really, really quickly. So now let's say you've done that. You've got your whole character. He's got clothes. He's rigged up. Eventually, you start getting into what are essentially character fixes, where you need to do things like pose space deformation. You want to, you know, remove intersections from the geometry. You want to create a bunch of poses so that your mesh moves in the way that you would expect. So again, in Houdini 17, we've added a whole workflow for doing that. So there's a whole suite of nodes to support this. But again, we've tried to make it a viewport-based workflow. And you can see in the top right, we have this new interface for creating pose layers, for layering together in different ways, for jumping to edit nodes and editing the geometry in the viewport, and then choosing how they're driven. In this case, the bones are angle-driven, and so the muscles blend, the poses blend as the bones change their angles, but you can actually drive it from any parameter in Houdini. And then full body IK. So something that often happens is that you have a very awesome rig that you've set up, and you want to do a very natural sort of pose with it, and that usually means moving many bones into a specific way. And what full body IK gives you is the ability to grab, say, the hand, pull it in a direction, and the character's whole rig moves along with it in a hopefully natural way. So here you can see it on this ant rig that when we pull the legs forward, the whole body comes forward. So the IK goes through the whole rig. The really nice thing about the implementation we've done for full body IK is that it's exposed in VEX, so a rigger can actually use their own implementation of this however they might like. but it's also possible to overlay it onto an existing rig. So a rig doesn't need to be generated with full-body IK in mind. It can be sort of superimposed on it at a later time if it becomes useful for parts of the chain. And it also works together with forward kinematics and single chain IK, even just using the pose tool. So just grab an IK chain, enable it in the pose tool, and you can work like this. And then grooming. So again, we've improved our grooming tools step by step over the years, and we've continued to do that for Houdini 17. And in fact, these tools are already being used in production. They're well liked. And what we really needed to do was just improve some of the core technology to make the way you interact with this just faster in general, especially when you're dealing with very complex grooms. And basically what that means is that we've taken the sort of core nodes and we've improved them pretty dramatically performance-wise, and we've added different masking options so that you have a lot of control procedurally over the look of your groom, and you can actually pretty much interact with a very high-res groom in the viewport with the OpenGL shader to get a really nice result close to what you actually will get in the end. But it's not just core technology, it's also new features. So this is recursive subclumping. And this is really for furry characters, generally speaking, but humans kind of have hair like this sometimes. Anime characters, I guess. And so the idea is that you can create a clump, and then from that clump, create subclumps. And this is recursive subclumps and clumps and clumps. And again, all working within the same grooming tools, so nice and fast and interactive. And so this is just a line built with those tools that I just showed you. This is not a simulation, I should point out. This is purely the groom deforming based on the skin. And even without a simulation, you can get some really nice results. But as I said, one of the great benefits of this workflow is that the VELLUM solver is embedded in the grooming tools, and that means that this groom that you've set up can just be passed downstream to the simulation for when you actually need the effects on the main and so on. And then sometimes you've got a character. Perhaps you've done a game cinematic and you have a very high-resolution character, but this character actually does need to eventually become a real-time character. It can't just live in cinematics with millions of hairs. So we've actually included a new set of nodes, a new node dedicated specifically to generating what are called hair cards. And the idea is you can start with a full-res groom of something like this squirrel, and then convert it into a hair card version. And the hair cards are essentially cards that follow the underlying groom, but are UV'd and prepared for texture maps, basically. So you can put textured hair on those cards and get a real-time approximation of your full-res groom. And once again, I'm going to bring up Cristin to introduce the next segment.
Thank you, Scott. Let's talk now about some of our bread and butter, RBD and destruction. There comes a point when every user of Houdini has the urge to blow something up, right? And it's not the learning curve. People just want to find out about how destruction is done with Houdini. And so it kind of makes sense for us to help you with that, to reduce that effort of reinventing the wheel, to help the student, the indie user, all the way up to the big visual effects studio. And we went through an important inflection point toward that goal with Houdini 16 when we introduced the Boolean SOP, the new Boolean SOP, which suddenly allowed this insane destruction of geometry data to be fast, reliable, almost fun. And so we're very happy to say that now about, just a year later, we have harnessed the power of that amazing Boolean SOP and combined it with a new Voronoi tool and with a bullet engine to create a new framework, which is a material-based framework for destruction. All right, this is the main piece that we're going to talk about. So this architecture, as Scott will tell you in a minute, comes with pre-fracturing controls, procedural controls for wood, concrete, glass. We'll deal with probably metal and other things later on. But equally importantly, it comes with artistic controls and with auto-generated constraint systems, so that we take away that pain, that fuss over the nitty-gritty, so you can focus on what's important. All right, with that said, here's Scott again.
All right. So when you're dealing with rigid bodies, there's something that is, you have a lot of urge to do, which is to make them look like they're bending, which is not what rigid means. But nevertheless, it's useful in a simulation to be able to do this. And Bullet has actually had soft constraints for quite some time, but we've never implemented them fully in Houdini. People would sort of use things like heavily dampened springs or pin constraints to get them. So now they're actually exposed directly in Houdini, and it really allows you to create simulations like this that were definitely possible in the past, but the soft constraint mechanism makes it so much easier to create this feeling that things don't just break apart, they sort of break apart and then hold together as much as possible. It allows you to create these really cool, almost bending simulations. And speaking of bending, you can actually emulate the bending of metal by simply fracturing, this vehicle into many pieces and using soft constraints as a way of deforming your actual geometry. So this is not FEM, this is not VELLUM, this is the bullet solver, but it's driving essentially a set of soft constraints to deform the metal here post-simulation. Convex decomposition. So the thing about the bullet solver is that it likes convex shapes. It does not like complex shapes. And that's good. That's what makes it fast and so on. But occasionally you do not have convex shapes. You have complicated shapes. So let's just imagine this sort of weird claw shape here. And you can see that a convex version gives you these sort of approximations. And so what the convex decomposition allows you to do is take a complicated object and break it into smaller and smaller pieces, which actually are convex. And that makes Bullet very happy. So you can see starting out with something not particularly useful and getting more and more fine-grained until you get to something that actually matches the original shape quite well. And this becomes even more obvious when you look at it in the simulation, where the simulation on the left is a nice simulation, but it's obviously missing a lot of the dynamic behavior you would get from a shape like that, where the one on the right is very much keeping it. And again, here using the actual render geometry becomes even more obvious. So there are ways to get Bullet to do this currently without using these convex shapes. There is a concave collision option. And the problem with that is that Bullet just does not work very well with concave shapes. So it tends to jitter, it becomes unstable, and so you correct that by adding more and more substeps. But then you're paying a very heavy price for not that much of an improved simulation. Whereas the convex decomposition gives you the shape that you want without paying that penalty of substepping and so on. So it works in a way that Bullet likes, which means that it behaves much more stably in the long run. Material-based destruction, as Cristin mentioned, this is sort of a new framework for setting up destruction scenes. And the idea here is that different materials fracture in different ways. Concrete breaks differently than wood. Glass breaks differently than concrete. And so not only do you want to shatter it in different ways, you want to build the constraints in different ways that make sense for the different type of material. And so what we've done here, this is a concrete example, is sort of harnessed a couple of different parts of Houdini and brought them together. So we have Voronoi shattering, which you're sort of accustomed to, and then we combine it with Boolean shattering. And what that does is it gives you a lot more flexibility to create shapes that are very difficult to create with just a raw Voronoi fracturing. And also on the right, you can see that it's generating the constraint geometry at the same time. And not shown here is that we also create proxy geometry. So in this one series of nodes, you're basically creating your render geometry, your proxy simulation geometry, and the constraints to go along with it. And again, as Cristin mentioned, this is really a framework. It harnesses a bunch of pieces of Houdini. So a new Voronoi fracture 2.0, which is, again, faster and more stable. We've broken apart some of our monolithic nodes to give you access to things so that you can make changes without having to recook results from the previous node. And again, we've split things into these different material types. And all of this is really just to give you more control, get to where you're already going faster, hopefully. So here's an example of the wood fracture and the constraints that are built with it. So obviously wood would probably have soft constraints and so on. So the constraints and the geometry are all built at the same time. You can get these really nice sort of woody bending, fracturing results. And also glass. So again, typically you do glass, use a Voronoi shatter, you're going to get a pattern like this. But by combining Voronoi with Boolean shatter, you can get rid of those sort of telltale shapes that everybody sees with a Voronoi shatter, and instead get a very believable looking fracture pattern. Again, with these tools built in, designed to help you get to this point as quickly as possible. Because usually the simulation is the hard part, and the fracturing is just, building up to doing the simulation. So if you have a really good input, hopefully your simulation will be better in the long run. And so here's just an example now of sort of all those pieces together in a pretty simple little house, just so that you can focus on how the different pieces act like the different materials that they are. So just by looking at them, you can see that wood breaks differently than concrete, glass breaks differently than wood. And not only that, the constraints themselves look and behave differently. So you can see how the concrete chunks have different glue patterns, different constraint patterns than the wood does. And again, the wood constraints attach to the glass, the concrete attaches to the wood. And again, this gives you a much more believable sort of way of fracturing the objects and simulating them. So even on a still, without any animation, you can kind of look at this and know what the different elements are. You can see that the wood has broken the way wood would. And also that we can keep all of the groups and attributes that you would expect, so you can put your render time displacements on the interior of the trunks, and really, again, break up that standard Voronoi kind of look. And, thank you.
Thank you again, Scott. This is just the beginning of the destruction framework. By the way, we have lots more work ahead of us, but we hope that the fruit of this first endeavor will be enough to get you excited and going with it. All right, so modeling. That's quite the endeavor. Eh? There's a lot that goes into writing a good modeler. Strong geometry tools, of course, goes without saying. But equally importantly, maybe more importantly, having a great workflow that helps the artist stay in the zone. And then when you have to marry that interactive feel and need of feeling fluid in the modeler with Houdini's inherently procedural nature, that fun is taken to the next dimension. So that's my way of saying that writing a good modeler in Houdini is a challenge. It's a fine balancing act, but we're definitely committed to it. And we aim with each release, including 17, to give you a good balance between improved workflows, like alignment that you'll see in a minute, and procedural stuff, because it's very important for us to advance that procedural agenda. And with Houdini 17, that speaks directly to the needs of UV generation. So that's going to be a very interesting part of this presentation that we hope you like. Anyway, this is time for me to pass it back to Scott to take you through it.
Thank you.
Thanks.
Okay. So in a lot of ways, modeling is a bunch of discrete tasks, right? So one of the most common ones is aligning things, taking a piece of geometry and aligning it to another piece of geometry. You do it probably thousands of times when you're modeling something. We had tools to support this kind of workflow in Houdini for quite some time, but it required you to place nodes. It required you to go in and type values into parameters and so on. And while that's fine when you're building a procedural network, if you're just interactively modeling, it becomes very frustrating. So we wanted to move some of that into a place where the artist could get at it more easily. And so here's just an example where we have these hands of a clock, and we have added something called alignment handles in Houdini. So we have these orientation handles that we can grab, and you can see I can select an axis and click a piece of geometry and automatically align that geometry to that edge. I can also grab the handle and hover over a point and point that axis at the point. And so this allows you to very quickly take a piece of geometry, align it to another piece of geometry, and then start working with it in that new alignment. So in this case, we're no longer moving it around, we're simply aligning it to the options on the clock. And again, all this is stored in the parameters. It's still nodes. It's just putting it into the viewport where you expect it to be when you're working with objects like this. And we've also taken some ideas from the network editor and brought it into the viewport. So let's say you've got a model like this. Occasionally, it's nice to be able to set up views in advance. And so now there's a hotkey to simply recall views, to store and recall views. And also, we've revamped our construction plane to actually have this idea as well. So we can quickly jump to a part of the model, drop a construction plane, and then all of our nodes are now aware of the construction plane. They will drop and align properly to it. So you can quickly work at object level or in SOPs aligning to this construction plane. And you can see here I'm just dropping nodes and aligning the text to the signs in these pre-set up locations. So again, the idea here is just to give you the tools that you expect and keep you looking in the place where you expect to use them. Modelers also often do something like this. They'll model up one section of an object with the idea that they're going to repeat it around rather than model it every time. And in order to do that, you really need to be able to have a handle that understands angles and snap to angles. So in Houdini 17, we've added handle snapping for both angles, scale, and translate. So now you can set a value and very quickly, again, all in the viewport, create an object like this, which is not a complicated object, but previously you would have had to go into your parameter editor, type 45 or 23 or whatever it was in there, and again, break out of that flow of modeling, which is so important. And then a long-time feature request is the idea of being able to work with multiple objects in their own local space. So here you can see one handle, we've selected two objects, we're moving them globally together. But if we turn off that global control now, we can move them along the axis. And this is just a long-time request that people have really been asking for. It helps with layout, it helps with animation, it's just an overall useful feature. We finally listened to all the cries and added it into Houdini. Now, a lot of the tools that I've been describing are working at very high level, right? Like moving whole objects around, basically. But a lot of modeling is this idea of, literally building polygons. And a while back, we introduced something called topo build, which was a way of creating polygons on the surface of projection geometry. In this case, we have a high-res sculpt and some low-res geometry that we're creating. And in Houdini 17, we've added a bridge tool that basically lets you fill in wide patches of geometry just by selecting the edges on either side. And a cousin to this is a new tool called Polydraw. And Polydraw is a very similar tool to Topo Build, except it does not require any projection geometry. And so this is geometry being built in 3D space. It works with the construction planes that I just showed, and it works without the construction planes. So you can create a piece of geometry like this very quickly in 3D without any underlying projection geometry. So again, this becomes a very low-level tool, the opposite of the other ones, where you're creating polygons one at a time in an almost sort of pick-and-draw kind of fashion. And then UVs. So UVs are a necessary evil. Nobody likes doing them, but you do need them. They are a necessary evil in CG. So we thought, well, can we help with this at all? Can we do any sort of automatic detection of these seams in advance? So we've come up with this tool called UV Auto Seam, and the idea here is that it generates the seams for you, what you will eventually feed into your UV flatten. The idea of this node is that essentially it analyzes your mesh, it tries to find the locally sort of flat areas, and then it gives you controls for merging them together to hopefully give you nice clean edges that you can then feed into your UV flattened node. And so here's just some examples of geometry that have been flattened and UV'd using the UV Auto Seam. You can see it creates some pretty nice shapes overall, and it gives you a nice flat result. So the idea here is that you can at least get this far very rapidly, and then of course this is just an edge group, which means that you can then just go and edit it, right? So it can get you this far, and then you can continue by hand if it's necessary. Oftentimes it is no longer necessary. However, it's still necessary. So we have improved UV flatten. We've added some visualizations so you can see how well the flattening is working in the viewport. And we've also added some tools for taking geometry that sort of has a quad layout and automatically turning it into a rectangular layout. And this is really useful for cleaning up edges, for straightening parts of the geometry, and just giving you a better UV layout overall. This can be useful when a texture artist has to actually start texturing these things, And it also can be useful downstream when you think about packing these UVs together, because squares and rectangles are much easier to pack into a smaller space than sort of oddly shaped objects. And so UV flatten then feeds into UV layout. And UV layout has basically seen a complete rewrite. It's almost a brand new tool. It has a lot of new options. We do not have time to cover them all. But here we have this similar object to the last one. I've color-coded these so you can see objects that are topologically similar. And now we can use this stack identical islands option, and it will take any geometry that matches, and it will put them on top of each other, because oftentimes you don't need unique details for those pieces. If you look closely, you'll also see it matches mirrored islands, so if you have two parts of a character, for instance, they'll still match. And then a really interesting option, which is allow stacking on non-group islands. Now, that phrase may not make any sense to you, but imagine you have a UV layout, a template UV layout, and you want new geometry you create to move into that template and match whatever is there. So it's kind of like taking pieces and fitting them into correct spots on a already created UV layout, which again, for film is useful, but extraordinarily useful for games where UV space is sort of at a premium. You want the best packed UVs you can possibly have. And another interesting feature is that we started, as this tool was rebuilt, it started using what's called exact arithmetic to make something very, very accurate, something that really, truly understands the shape of things in 3D. And that actually allowed us to do something really interesting, which is start laying out things that are not UVs and start looking at things like the position attribute instead of a UV attribute. So here's an example of taking a cluster of 3D objects and then packing them inside a 2D mask. So they retain their 3D shape, but you can put them inside a layer, essentially. And this can be really powerful. You can imagine doing city planning with this, putting footprints and packing buildings inside of it. So up to this point, again, it's been very much about interacting in the viewport. And if you're a tool builder, if you're somebody building tools for somebody else, something that you very often want is to create a more robust interaction in the viewport than what's typically provided to you in Houdini. Typically, you need to know C++, you need to go into the HDK and start modifying things, and that takes a lot of technical know-how, and is also sort of tedious to do when all you want to do is have some control in the viewport. So in Houdini 17, we have added a Python API for getting control of things in the viewport and adding custom interactions for things like handles, mouse events, and so on. So here's just an example of two tools that you've kind of already seen, but now being driven by this Python script. So all the interactions of clicking and dragging things in a handle are actually handled by Python. In fact, this was written by two examples written by our technical documentation team, so that you have something to get up and running with. But you can see essentially, a page worth of Python to let you build custom interactions in the viewport, which is much nicer than a page worth of C++. Probably a lot more. Now we're going to talk about terrain, and I want to bring up Cristin once more.
Thank you, Scott. Originally driven by the needs of the gaming community, the terrain toolset that we introduced in Houdini 16 last year was readily adopted by gaming and non-gaming artists alike. It was an instant success. It's used in production in very many places, and we're only happy to improve it. One fact I want to point out is that this interesting cross-pollination of Houdini's feature set within our community is one of the nicest things to see, which is why sometimes we have a hard time to label something for just for gamers or just for motion graphics or just for lighters, because people jump in and find interesting ways to use it in a completely different area or a completely different field. Anyway, our long-term goal for terrain is to build a very strong tool set for large-scale environment creation with proper, optimized way of dealing with tiling, data optimization, smooth outputs to games, and so on. But today, we're happy to introduce you to the second iteration of our terrain toolset, which focuses primarily on the #1 request from the community, which is erosion and debris quality. There's such a thing as bad debris and good debris. Houdini 17 is all about good debris. It also comes with some bonus features. One is called tectonic distortion, and the other one, collision-aware multi-scattering. And again, back to Scott.
All right. So the original set of terrain tools did have erosion tools. There was erosion simulation in there. It tended to give soft results. So you did get erosion, you got kind of what you expected, but it took extra work to get to the level of detail people were expecting. You had to sort of do multiple layers of erosion and really work to get it to look the way you would expect. In Houdini 17, we've rewritten the erosion simulation tool from scratch. And so now the idea is that it can very rapidly, very aggressively get you the detail you're looking for with far fewer iterations, solver iterations, than it's taken in the past. And so the idea is here you can use the solver to generate all kinds of erosions, sort of like wide rivers, and then these very tiny fluvial vein-like indentations in the surface. So the idea is to get you to very high detail erosion more quickly than you could in the past with a much more robust solver that has much more user control as well. And here's just an example from one of our users in our alpha forum, creating a sort of Mars-like terrain using an early version of these new terrain tools. So the reality is, though, that you don't just want anything and then put erosion on it and say that's good. You want to have some more control over it. You want to be able to distort parts of the terrain, essentially art direct it into different shapes. We already have a whole suite of tools for doing this, including other distortion tools, but in Houdini 17 we have a new sort of set of tools that basically take a base layer, which is to say your terrain, and then a control layer, and then it lets you modify the terrain in different ways. So this is the smear mode. So you can see wherever that mask is painted, we sort of pull in the geometry, we draw it together. Now this is a very exaggerated version of what you might do with this mask, but if you look at it on an actual piece of terrain, you get some really interesting effects, like we can find these sharp peaks and pull all the geometry toward the sharp peaks. We can also kind of do the opposite and find those sharp peaks and instead sort of pull them apart, stretch them out, so you get sort of a more boulder-like appearance rather than this sort of sharp Swiss Alps appearance. Another mode is swirl mode. And so swirl takes your mask and uses the gradient to understand which direction to sort of swirl around. And it creates this really interesting effect when you really push it. In fact, I can definitely imagine effects people who do not care about terrain using this for some really interesting effects because it looks really cool. Having said that, the goal is to be able to add this onto a terrain. So here again, you can see that we're using essentially the height as the mask here. So we're sort of swirling the fine details over the surface of the terrain. And this is really nice for creating sort of volcanic looking things that almost have a fluid quality to them. Or you can imagine a very sort of stylized terrain using this to really distort the geometry or the terrain in interesting ways. And so really the idea here is to give you a bunch of tools that combine together to let you create really interesting high detail terrains in ways that were maybe possible before but required quite a lot of work, and now are sort of at your fingertips using the stock nodes. So single and multi-scattering. So the idea here is that obviously if you have a terrain, real terrains have all kinds of stuff on them. They're not just the bare rock, right? There are trees, there are rocks, and so on. And we did have tools for scattering objects on terrains, but they were limited in a couple of ways. And one of the ways they were limited is that when you painted your mask in 16.5, you would get the trees where you painted them, which is exactly what you want. But you can see that the more I paint and the more I add, the trees kind of move around. They shift around in space. And sometimes that's fine. You don't care. You don't mind if that happens. But if you're working in something iterative like a game and you place some trees in your environment, you sort of want them to be locked down. You don't want them to shift around after you start making new changes. So in Houdini 17, everything stays locked to the terrain. Once you've painted something, it's going to stay there for the most part. But it's not just about scattering things and changing the way they look. It's about building sort of a hierarchy of objects. In the real world, things aren't just scattered randomly. They actually have relationships to other objects. So a very simple example is we have these rocks, and we're placing them down in our environment. And then around those rocks, we want to have trees growing. And we don't want the trees to live where the rocks live. They should live next to the rocks. And then we have bushes, and they're going to live between the rocks and the trees. And then eventually grass. And if you look at the footprint diagram on the left, you can see how natural it looks, right? It doesn't look random, it looks structured. It looks like there's a hierarchy. And this is even more blatantly obvious when you compare it to what you would have gotten in 16.5, where essentially you're just getting random scatterings where points are overlapping other points, and there's no actual structure to anything. Whereas on the right, you get something that almost starts to look like an ecosystem, even though this is using the bare minimum of rules here, just each layer avoiding the previous layer. But even just that simple rule gives you a much more structured look, something that is nice and clean and can be worked with right away, as opposed to all the cleanup and moving of points you would have to do in 16.5. And once again, I'm going to bring up Cristin to talk about our game dev tools.
Thank you. Supporting the game dev community has become a constant and very important focus for our company and for the R&D group. And seeing how many of these game-intended features have been readily adopted by non-games people has more than validated our decision to dive into gaming territory. Now, you've already seen a whole bunch of features tonight that could easily qualify as game dev features. The UVs, the terrain just now, some aspects of modeling and whatnot. So in this chapter of our presentation, we want to focus on a couple of major advancements that sit more squarely in the game dev space. Among them, 2 brand new Houdini engine plugins that we're very proud of, and also that tool shelf, which you see on the slide, which really is just the tip of the iceberg. There is a team, a growing team of games TDs at SideFX that are putting together game-related tools at a dizzying pace. Scott will show you more about them. And the reason I want to mention those is that not only do they address immediate production needs, those guys are so finely tuned into the needs of that community, but the intent for us in the greater R&D group is to pluck some of the most valuable tools that they create and bring them into Houdini proper. So that's the long-term goal for us. Anyway, Scott, you're on again.
Thank you.
Thank you.
So Houdini Engine was released quite some time ago now for a variety of platforms, Maya, Unreal, Unity. And now in Houdini 17, we've added 3ds Max to the list of software supported by Houdini Engine. And you may have heard in the past that there was sort of a 3ds Max plugin out there. And with Houdini 17, this is, in fact, a SideFX owned and supported plugin that will be supported into the future. So you can feel confident in diving in and using it right away. But let's talk about the Unity plugin. So we've done a lot of work on the Unity plugin, and I don't have time to talk about all of it. But one of the key features is to take these terrains that we just talked about, bring them into Unity in a unified kind of way so that we can take the actual height field data and plug it directly into the terrain system that already exists inside of Unity. So this is a truly hybrid approach where Houdini Engine feeds the Unity engine's built-in terrain tools, which means you can use Unity tools to modify the Houdini terrain, really bringing these tools together in a really interesting way that just was not possible before. Required baking steps and texture maps and so on. This can happen sort of live. And then we've also continued to make sure that the interaction in Unity with these assets is very clean and artist-focused. So you can see here these awesome tools showing out how easily you can interact inside of Unity in a sort of artist-friendly way, while under the hood, Houdini Engine drives a series of complicated assets. And here we have the 3ds Max plugin. This is actually not even really a games context, it's architectural visualization, but you can see bringing in a simple geometry asset that builds interesting shapes like doors and windows, and inside of 3ds Max, right inside the UI that you would expect in a familiar way if you are a 3ds Max artist. GLTF, so this is a format that's come about that's become very popular. It's essentially a way of storing geometry, shaders, and textures sort of all in one file. And we actually got a lot of requests for being able to import these files. So The interesting thing is we started with export. This is just a demo showing the ability to take an object shaded and built in Houdini and bring it into other contexts, things like Microsoft's browser, Facebook, or obviously game engines as well. But we also did the import side as well. So we can bring in these GLTF files, maintain all the shaders, all the connections you would expect, and we can sort of flatten the hierarchy into a single piece of geometry with groups, or we can split things apart into a full hierarchy to maintain the GLTF format's hierarchy. And that means that you can do true round tripping of these files, bring them out and into Houdini, and hopefully keep everything exactly the way you created it. And the production tool set. So this is what Cristin was sort of alluding to about the game dev TDs and the tools they're building. So inside of Houdini, there's something called the Game Development Toolset. This is an example of one of the tools. It's called the Game Res tool, I believe. And the idea here is that you take a very high-resolution photogrammetry object and you bake the high-resolution detail to a low-resolution mesh using a very simple tool that does automatic UVs for you, using the technology from Houdini 17, as well as texture baking and so on, all in one little tool. The great thing about these tools is that they're constantly updated. So, they had to wait for Houdini 17 to be released in order to put these tools into the game dev toolset, but now they are. So they're constantly iterating on these tools. And the idea here is that they are sort of laser focused on the needs of game development. They are solving actual real problems as quickly as they can, and these tools are available at any time from that tool shelf. You can use them to download from our webpage, from GitHub, and use them directly inside of Houdini. So this is a really awesome collection of tools built by our awesome game dev team. And like I said, laser focused on the needs of actual people in production. So these are great tools. Go and grab them. And one more time, I'm going to bring up Cristin.
I want to make my intros short and sweet. All right, when we talk about the bread and butter of Houdini, we mention destruction and fluids in one breath. And there's no accident that we've left fluids as the last chapter of our presentation tonight. They're very important. And first, I want to thank you on behalf of SideFX for how much you've embraced fluids out there. Really, the adoption has been phenomenal, and we see amazing work done by you guys in everything from film to advertising, motion graphics, games, everywhere. And that motivates us to make it even better, to up our game with every release. And this is our promise to you, that every Houdini release will have something to do with fluids. There'll always be an enhancement there, and we'll always listen to you. And talking about listening, about what you need there, and hopefully about Houdini in general. But with respect to fluids in particular, for Houdini 17, we've tried to address two of your biggest requests. One was OpenVDB sourcing in fluids, and the second one, the quality of white water. The outcome of that really upped the original mandate. I hope I'm right. So the first one led to a brand new workflow for Pyro setup and simulation. And the second one led us to a completely new solver for white water. It is brand new with a much more organic look, as Scott, again, will demonstrate. Thank you.
So if you're going to run a fluid sim, whether it's Flip or it's Pyro or Smoke or anything, everything starts with sourcing it, right? You need it to come from somewhere. And the reality is this could actually be a bit of a painful process in the past because it could be surprisingly slow. So we took a look at that, and obviously the biggest bottleneck was this lack of OpenVDB in our sourcing tool. So on the right, you see the new version of sourcing these particles, and you can see by the time we've gone through the entire frame range, we've gone up to like frame 10 or something in the original. And this could actually cause the fact that your source may actually be slower to cook than your simulation, which is obviously not what you want. That should definitely not be the slowest part of your setup. In this case, it's around 40 times faster than the original simulation, or the original setup. And so as we started investigating this workflow and updating the tools to be faster and so on, it started to make us rethink about ways we could use this inside the solvers. So for instance, if we rethink sourcing a little bit, it makes us be able to do things like this. Say like, well, what if I want to inject color into my pyro simulation? I need a way of sourcing the color somehow, so we need to rethink sourcing. We need to build it into the solver itself, but we also need ways of getting it into the solver in useful ways. And that led to the idea of a whole rethink of the pyro workflow. So the first thing that's different about the pyro workflow is that it's point-based, it's particle-based. It eventually becomes fields, it becomes volumes, but what we found from customers is that most times they were running a particle sim, or they had some sort of geometry animation, and they were using that as their source. They were not generating volumes from scratch and manipulating them. Also, things like attributes and points are a lot easier to manipulate than volumes are. We have a gigantic suite of tools for manipulating that kind of data. So to start with, we made a new pyro source, which is really about generating all the appropriate attributes that you will need to do these types of simulations. Then we started building helper nodes like attribute noise. Everybody who's worked in Houdini in effects has probably put down a VOP network and put down a noise VOP inside of it. And so we finally said, why don't we just make a SOP that does that for you? But in fact, we've actually made it quite a bit more interesting. You have very fine control over the distribution of these attributes, and you'll see a little later some interesting workflow tied to that. And then finally, volume rasterized attributes, which is a way of sourcing the particles or the geometry into the actual volumes. And the nice thing is this does it for you. You list the attributes you want to rasterize, you get the volumes that correspond, and you also have control over how those are sampled into the volumes if you have some specific needs. And just before I move past this, I want to point out something interesting that was added to the middle mouse button, which is the ability to actually go ahead and see what attribute has changed from the last time you looked at these attributes. So you can see these crossed out values showing that like they used to exist and now we've deleted them. And you can also go into essentially a debug mode and show really deep information in here. And this is a bit like the modeling workflow we talked earlier, where we want to put this somewhere closer to where the artist is working without constantly having to go to the geometry spreadsheet and look back and forth between nodes. So again, it's about simplifying that workflow and putting the tools right where you expect them to be. But let's take a look at setting up one of these particle sims. So here we go. We've got this particle simulation. It's your standard sort of explosion-y thing. And we're just going to go ahead and use the billowy smoke shelf tool to set it up. And we get something that looks, whatever, looks okay. So here is the new fluid source, which we don't really have time to cover, but that is also new. And so what we want to do now is, let's say, add some noise to the temperature. So we now have this new visualization action button that you can press to visualize an attribute directly on the geometry. So here you can see we're visualizing that noise, and then I can just turn that off. So it's not a matter of dropping visualizers. And then we see the result playing back in the viewport. It looks a little different. We've changed the temperature. Let's go ahead and add some color now. So I'm just going to grab a node I already made that turns this into sort of clown colors. And now we get this sort of rainbow vomit of colors. And we're just going to add that into the simulation using our new shelf tools for adding color. And you can see that it's added the attribute for color. And then as soon as we hit play, that's now in the solver. There's no extra setup. The shelf tool takes care of it for you. And the viewport displays the color in the viewport. Now, of course, you're not likely to actually do that with the color. What you're more likely to do is create interesting, dusty, sort of dirty-looking colors. And what's cool about that is that it actually makes your simulation sort of automatically look nicer and more interesting because it's not a uniform color, it's not a uniform gray. It sort of breaks up and adds texture to your smoke without actually changing the simulation at all. You get essentially the same sim, but with a more interesting sort of textural look. And just to show you again the difference in these two workflows, again at the bottom you see we go through the entire frame range before we've gotten to sort of frame 20 or something of the one above. This is about 10 times faster, what you're seeing here, but in practice, it was occasionally as much as 100 times faster. So it really depends on the type of source that you're giving it, but you should see a huge improvement in speed of these sourcing tools, which again is really important. So here's just a render of those two setups that we made, and you can see that the Pyro shader has also been updated to take these color fields directly inside them as well. So there's no extra setup in getting this to work. You add your color, it goes into the sim, and you're sort of ready to go. So retiming is something that comes up quite a bit in effects. So even in the example I just showed you, it would not be unusual for someone to say, like, oh, that's good, but can we make that initial burst, just a little bit punchier, Can we make that happen a little faster? And in this simulation, it would be very easy to just resimulate it. But sometimes, this is like a 2-day-long simulation, and you don't want to do that. So instead, you want tools for doing the retiming post-simulation. And so in Houdini 17, we have added a new retime node that allows you to take a base volume sim and speed it up or slow it down. And this is done with can be a linear interpolation, but it also takes things like velocity into account to make sure things bend and move the way that you would expect between frames. And so in the past, what people would often do is like bake out, a whole bunch of subframes of smoke so that they had some flexibility with speeding up or slowing down. But that's sort of a painful process and tons of data. And this actually gives you the same sort of ability, but just by generating the data for you when you need it. And you can see that there's no sort of popping, there's no weird artifacts. It actually very smoothly interpolates the data and retains a lot of the detail that you see. And then this really just opens up the door to all sorts of interesting sort of motion graphics-y type effects, interesting effects in general. And even though I'm just talking about volume retiming here, this actually applies across the board. So this is geometry as well as volume, so you can retime flip fluids, you can retime particle sims, and obviously character animation and so on. So narrowband. Narrowband was very recently introduced in Houdini as a way of optimizing large-scale fluid simulations. And as the name suggests, it's a narrow band, right? We simulate the particles in a narrow band around the dense fields. And that's great. It's a great way to optimize these types of simulations. But there is a bit of a problem, which is that if you have information on those particles, and that somehow gets pushed into the deep part of your simulation, you essentially lose it. So here's just an illustration of that idea. Let's say we had color on our particles. Obviously, once it moves past the narrow band, there are no particles in there, so you lose it. In Houdini 17, we've added the ability to advect custom fields inside the narrow band, so beyond the narrow band, inside where only the field data, where the volumetric data exists. So you can smoothly transition an attribute from the particles into this interior volume. And while this is a really interesting kind of neat result of this sort of ink inside the fluid, you can imagine using variable viscosity, which would have been impossible with narrowband in the past, but maintaining the viscosity inside. So if you have very dense or highly viscous fluid in the middle here, you don't lose all of that information. So in the previous version of narrowband, if you want to do a river simulation like this, you could do it. But there was actually a pretty high cost. The narrowband calculation for sort of colliding with collision objects like this, as opposed to just a deep tank, was pretty costly. But in Houdini 17, we have basically removed that barrier. It's something like 40% faster than it was when you're dealing with these types of collision objects. So now it really becomes feasible to take something like what you see on the left and create a narrowband simulation of it like you see on the right, which gives you a huge savings in memory and very often an increase in performance as well, which, as you know, with these high-resolution simulations is vital. And now whitewater. So we've had whitewater, I think, since Houdini 11 or 12 or something like that, and it's been your standard sort of particle-based system. We've made some updates over time, but there's sort of one driving issue with the whitewater solver, and that was that the particles didn't really know about the other particles. Whitewater existed in a vacuum. It was just typical particle sim, essentially. And in the real world, foam and spray and stuff actually interacts with itself, obviously. So with Houdini 17, we've, as Cristin mentioned, completely rewritten the whitewater solver. We've added interparticle forces using something called pop fluid forces. We've also added something called repellents, and those help create these realistic sort of foam patterns on the surface of the waves. You can see that kind of cellular patterns that show up on foam as it rests on the surface of a fluid. And we've also just changed the way you interact with this. So again, the particles evolve over time from state to state. They don't sort of live in one state or another as they did previously. Also, we can directly push it into our ocean deformer. So there's no simulation really happening here at all except the whitewater. So this is just a deforming ocean with the whitewater tools being run on it. And you can see how it gives you a much more realistic look than just a simple particle sim would give you. You can see that cohesion, the clumping of the particles together, and the way they rest on the surface in a much more natural way rather than sort of almost peppered on the surface as you would have had in the past. And so here's just sort of a beauty shot of some spray to really show the detail. And what's interesting here is that this artist has taken advantage of that idea of the lifespan that I was talking about. The idea that rather than having sort of hard states, which is what we had in the past, things like bubbles were bubbles, and then they turned into foam, and then they could turn into spray. And there were these hard divisions between those different levels. In the new whitewater solver, it's more of a continuum. That lets you do effects where you say, oh, I want to affect things when they're this close to the surface, or I want to affect them much later in their lifespan to create these kind of turbulent wind effects. And again, the fact that the particles can interact with each other using these pop fluid forces lets you do things like this. When you freeze frame this simulation and see how much interesting information there is in there. This is not just a cloud of particles. These are particles that make some kind of sense. You can see them sticking together. They become clumps in some places. They become strings in other places. And this is really how you get a realistic look out of something like foam and spray. And it just wasn't possible previously, and now the default whitewater solver will give you effects like this. And then finally, we want to end on just an example, again, of showing how different you can make the whitewater look. So in the top left, we have a pretty diffuse sort of explosion of whitewater. You can see some clumping, but as you go more and more with these forces, you can see in the bottom right this ability to sort of pull stuff together. It's almost like a viscous simulation now. So this gives the artist tons of control over the look of their fluid, and under the surface, we're doing a lot of work to make sure that it all makes sense in a sort of physical way, instead of the way things behaved in the past. And that's pretty much it. I'm going to bring up Cristin one last time. So thank you all very much.
Thank you, everyone, and thank you, Scott, for this amazing marathon presentation. Yeah, that was a lot to cover, and the list actually doesn't stop here. There are more features that we'll leave you to discover on your own. And there's one particular feature that we didn't cover that I want to single out, and that's the integration of NVIDIA's optics denoiser into Mantra IPR and batch rendering. Now, that's a very cool feature and definitely useful. But the reason I wanted to bring it up is because it holds a much greater significance to us, and hopefully to you in the future, as it is an early foreshadowing of a major new architecture that we're very busy developing in R&D these days. You've heard of it possibly as LOPS or Project Solaris. It's an architecture that goes straight to the heart of lighting and rendering, and in one big swoop takes Houdini's proceduralism, it combines it with GPU-accelerated workflows across the board, dedicated artist workflows, and it weaves all of that into a live and native USD core. But that's a story for another day. In the meantime, please explore Houdini, all of Houdini, and we do hope that you enjoy Houdini 17. Thank you so much. And just before we go, allow me please to tip off the hat to the great R&D team at SideFX that have made this software release possible. Thank you. They deserve that. And also to our alpha and beta testers, always uncompromising, always uncomfortable. Don't change that, please. We love you. And also to you, our Houdini family. Thank you again. Good night.